Okay, let's get started. Welcome to lecture 12. So the main focus of today's lecture will be Forney's GMD decoding for concatenated codes. Forney designed GMD decoding to be able to decode all the way up to half the minimum distance of concatenated codes. Yes, and time permitting, we might begin our discussion on graph-based codes, in particular expander codes, towards the end of the lecture. So let's quickly recap what are concatenated codes. So we had two codes, an outer code C out, which was say an N, K, D, Q code. You took a K symbol message over an alphabet of size capital Q and encoded using the outer code. And then then you looked at each symbol itself is a symbol from Q to the power K. We are working in the setting where Q is actually equal to small q to the power K. So we can view the inner code. The inner code Cn is a NKDQ code. So we could in particular view each of these blocks as a message for the inner code and apply the inner code on this to get an N symbol message for each block of this one. Therefore, the total length is going to be, this total length will be NN. So that's the concatenated code. It's a code. So the total concatenated code, C concatenated or composed, whatever called, was an NKK DD Q code. And last time we saw the vanilla decoding for this, which will let you decode all the way up to DD by 4. That was just apply the first the inner decoder and then apply to it, then apply the outer decoder to this. And we saw that this could handle up to be DD by 4. And this itself was useful for certain applications. But strictly speaking, one should be able to decode all the way up to DD by 2. And Forney showed that under certain, if the outer code has some specific properties, then one can do this. In particular, what did Forney? So what did Forney wanted? Forney's requirements for GMD decoding are the following. GMD, this is short for generalized minimum distance decoding. So he wanted the following properties: C out, which was the outer NK DQ code, comes with a decoder. Let's call it dec out, which can handle not only errors, but also erasures, which can decode from E errors and yes erasures provided 2E plus S is less than D. Okay, that's quick. Okay, so we wanted to do Forney's GMD decoding. We want to decode from this concatenated code, which the concatenation process like this, and it goes to a channel in which the utmost DD by 2 errors. And I'm going to state that we can do this decoding provided we have a decoder for the outer code and the inner code. The inner code is standard, it can be any decoding as long as it can handle up to the unique decode errors up to the unique decoding radius. The outer is not the standard one. It's not just E errors, but also it can handle both errors and erasures. It's a combination of these, as long as twice the number of errors plus the number of erasures is less than the minimum distance of the code. And we saw that Reed-Solomon decoder with the Reed-Solomon code with Burle-Welch-Burle-Cumb decoder is one such. This one. Okay, given these, how does Forney go about doing the decoding? So you have, this is, so I'll first tell it pictorially and then we'll actually write down the formal description of the code. Therefore, this was the received word, which has utmost DD by 2 errors. Therefore, there's a unique code word close to it because it's made less than half the inner distance. So we first apply the inner decoder on each of the blocks, sequentially, parallelly, whatever, apply and get the Z1, Z2, Zn. Now in the vanilla decoding, we would have applied the outer decoder to this Z1, Z2, Zn in one shot. But no, what we are going to do is we are going to find out with what confidence do I know each of these Z1, Z2, Zn. So we find out if Z1 was the actual, if Z1 was in fact the message that the right guy here, what is the distance between Z1, the encoding of Z1 and the corresponding thing over here? And based on that distance, that gives us some confidence measure. We are going to erase this coordinate. So we come up with Z1 to Z1 tilde, Z2 tilde, Zn tilde, which are just Z1, Z2, Zn with some of the symbols being erased. And this erasure is based on this confidence parameter about how close the encoding of this is to this long string over here. And then we apply the outer decoding algorithm, which can handle both erasures and errors. So out here, some of these things are erasures like this. Okay. Now so that's this one. We actually wrote this algorithm explicitly. So let's write it, let's recall it and do the formal this one. So what's the GMD decoder? So the GMD decoder. So its input is R1, R2, Rn in Q to the K, Q to the M to the N, where each Ri itself is of the form Ri1, Rin in Q to the N. And the algorithm, so step one, there's an outer face. There's an outer face and there's an inner face. And how does the outer face go? The outer face goes following basically for each, there's an inner face and then an outer face. There's an inner face. So for each I in N, we first run decoder inner on Ri, which is Ri1, Rin, to obtain Zi, which is a Zi1 up to Zik, which I view it both as an element of capital Q as well as an element of which is isomorphic as well as an element of Q power K. But we don't stop at this. We now try to find out what's the confidence of the Zi. Basically, we compute this Ei, which is the minimum of the distance of C inner of Zi with Ri. whatever that is, and d by 2. So strictly speaking, it's just the distance. If ever the distance is more than d by 2, we just truncate it to d by 2. That's what. So this is sort of the confidence measure, which the closer EI is to 0, we are more confident that ZI is actually the correct code word. It's closer it is to d by 2, there are more errors in it, our confidence in it reduces. So that's the inner phase. And then there's an outer phase, which does the following. It does basically for each I in n, it now goes around and tries to erase some of them based on this confidence measure. How does it erase it? It says for each I in n, set zi tilde to be equal to question mark with probability ei by d by 2 and zi itself otherwise. So for each outer block symbol, you go and toss a coin which with probability 2 ei by d, toss this coin. If it comes out heads, erase it, otherwise retain it. So that's the first part of the thing. And then run decoder out on z1 tilde, z2 tilde. Sorry, this is z. Yeah, so this is zik. That's right. Zn tilde to obtain m1 tilde, mk tilde, which is a thing in q per k. That's the entire algorithm. So questions on the algorithm. So first, we'll do two things. This algorithm, firstly, we have to analyze the algorithm. We have to understand why does this algorithm perform correctly. And then there are few not so satisfactory parts of the algorithm. It's a randomized algorithm. And the analysis which we'll show will make it work only in expectation. We will now then do things to actually completely remove the randomness from the algorithm and make it a deterministic algorithm. So we will do two things later on. But first, I want to ask you, is the algorithm clear to you? Are there any questions with respect to the algorithm?
Like, just to be sure, we can again use this, I don't know, this ensemble, Rosencraft ensemble here, or how is it called? Each inner code for each.
Oh, so you could have used the Rosencraft ensemble. You could have used this. There's no reason for us to have said all the inner codes are the same inner code. We could have used a different inner code, in which case you would have used the decoder for, you need a different decoder for each of the inner decoders. It won't be a single decoder. It will be the decoder corresponding. The same algorithm will just go through.
Yeah, I thought so. That's
Yeah. So that works. We could have used multiple inner decoders. It will just replace what Pavel's question. This guy will. So if you use different inner codes, you will have to use different decoders corresponding to the different inner decoders. But the inner code is never an issue for us. It's a very small code. Therefore, even the brute force decoder works for us. You don't need efficient decoders for this. If you have efficient decoders, well and good. Even the brute force decoder works. So first thing, let's see. So first we'll see the analysis of this algorithm and show in expectation, whatever that means, that the above algorithm decodes correctly, provided the total number of errors is less than TD. That's what we'll do first. Okay. Now, so let's come up with the proof of the analysis. So let's come up with some notation. Let's define EI tilde to be the number of errors in the ith block. Notice EI, recall EI was the distance between C inner ZI and RI. Actually, it was the minimum of this and D by 2. So EI tilde is the actual number of errors. So in that sense, summation EI tilde I in N is the total number of errors. EI need not be EI tilde. EI is EI tilde only if the number of errors in the ith block is smaller than small d by 2. Only then will the two errors match. You could have erased the ith block completely. You could have made all sorts of errors, in which case EI tilde need not be equal to EI. So I want to make sure everybody understands the subtle difference between EI tilde and EI. EI tilde is the actual number of errors that happen in the ith block. EI is what the algorithm perceives is the number of errors. The minimum of that and d by 2. So these are two different quantities. These need not be the same quantity. Okay. But we'll try to ask, when is this the same quantity? When is this not the same quantity? Now, if in fact Zi is equal to Xi, or that is equivalently C inner of Zi is equal to Yi, that means in fact the closest code word to what the algorithm did decode was the correct object. Therefore, EI, then in this case, we do have EI equals EI tilde. And they are both less than d by 2, or less than or equal. Okay, that's one case. The other case could have happened. The algorithm decoded it, but Zi was not equal to Xi. So there was something that was close to this object, but the actual errors were so much that actually the right object is Xi. So there was some Zi was the thing that was within d by 2 of this one. But on the other hand, the correct guy was more than this. Therefore, in this case, you'll know that EI tilde has to be greater than or equal to d minus EI. Why do we know this?
Distance from Z to forward 1 is EI, and distance from Z to forward 2 is EI.
So this is just triangle inequality. So there is the what you perceive as Yi, then what is C inner product of Zi, and the actual is C product. Sorry, this is not Yi, this is Ri. C of Xi, which is equal to Yi. So this is what we have been calling. This is what we have been calling EI tilde. Whereas EI is this object. Sorry, the other way around. This is what we call EI, whereas this is EI tilde.
Yeah. The tablet screen sharing thing is
Stop. What's going on? Let me. One second. So why did this happen? Sorry. This. Yeah, it should connect now. Let me see. Okay. So what's happening here? RI is the word that you have received. RI is the word that you have received. It's a corruption of this particular object. But the decoder thinks this is the closest object and recovers to this. In one case, in the first case, these both are the same object, therefore EI is equal to EI tilde. Otherwise, you know that this distance is EI, this distance is EI tilde. Triangle inequality will tell you EI plus EI tilde has to be at least D, because the distance between these are both code words. They both have to be at least D apart. Therefore, EI tilde is greater than or equal to D minus EI. This is okay. This is one of the crucial observations for us that we will need. That is, whenever it makes an error, whenever the inner decoder makes an error, the number of errors that happen there is larger than D minus EI. Okay.
Right, isn't on the picture EI and EI tilde switched?
No, EI tilde is the number of errors in the block. So this was the original code word, and RI is this. Therefore, this is exactly the number of errors that happened. This is what I recovered.
Oh, yeah. I switched
The
EI tilde and the EI for myself.
Yeah. So X and Y's are the real message. The Z's are happening all in the decoding phase. Okay. Fair enough. And this just follows that because the distance between these two is at least greater than or equal to D. And hence EI plus EI tilde has to be at least greater than or equal to D, and that's why you get this. So this will motivate us to define this following object. So we'll define this for all I in N. We'll define this random variable called UI. UI will be equal to 1 if the ith block is erased. It's a random variable. The ith block is erased. And it is, sorry, let's keep UI to be 1, just UI, and 0 otherwise. So UI is just going to tell you whether I'm going to erase the ith block or not. VI is going to say is 1 if ith block is not erased and xi is not equal to zi. That is actually the ith block is not erased, but this symbol is actually an erroneous symbol. The inner decoder has decoded it incorrectly. The outer decoder has to fix it, and 0 otherwise. Okay. So look at you. So UI and VI are random variables based on how the coin flips have happened, because it tells you which blocks are erased, which blocks not erased. Now it's sufficient if we show expected value of the sum of over all I in N ui plus 2vi if this quantity is less than, what do I want to show this? If this quantity is less than 2d, then I'm in good shape. Then the outer decoder can handle it, because what is it? The expected number of UIs is exactly the number of erasures, is the expected number of erasures, and the expected number of VI is exactly the number of errors.
Should be D.
So if this
Doesn't
sorry,
it-
this is D. This is D. Yeah. So if I manage to show this, I'm in good shape.
Yeah.
So this is what we'll try to analyze. We'll try to show that expected UI plus 2VI is less than capital D. Questions? Okay, so let's focus on a particular I. Focus on a specific I in N. The claim which we will prove is the following claim. We'll show that the expected value of UI plus 2VI will be less than EI tilde 2EI tilde by D. Notice that once I prove this, I'm in good shape. The claim implies summation I of expected UI plus 2VI is less than summation 2 by D EI tilde, which is exactly 2 by D times the total number of errors, which you assumed was always less than DD by 2. Therefore, this will be D. The claim implies this. This one. So all we need to now prove is the proof of claim. Fair enough. So we'll do it on a we'll do it on based on two cases, based on whether the ith block has been decoded correctly, based on whether ith block has been decoded correctly by the inner decoder. In particular, so the first case will be xi equals zi. So the ith block has been decoded correctly in this setting. So in this setting, notice that vi is always 0. Vi was said if it is erasure and it's an error. It's never an error in this setting. Therefore, irrespective of whether it's an erasure or not, vi is always 0 because it is correct over here. It could have been erased, but vi is 0. But what is ui? So expected ui, but in this case, vi is 0. Here now vi is 0 and ei is equal to ei tilde in this setting. But what is expected ui? Expected ui by definition is exactly 2ei by d. That's how we set it up to be. That's a probability of erasure, which is equal to 2ei tilde by d. In this case, we are fine. Now let's look at the other case in which xi is not equal to zi. Here, from our observation, we know that ei plus ei tilde is greater than or equal to d. What is expected ui? Expected ui, as always, is just 2 EI by D. Expected VI is 1 minus 2 EI by D. Those two put together will give you expected UI plus 2 VI is what? Is 2 minus 2 EI by D, which is exactly 2 into 1 minus EI by D, which by our choice of this one is less than or equal to 2 EI tilde by D. And hence we are done in this case. That's the end of claim, and hence the conclusion of this is GMD decoder decodes from less than DD by 2 errors in expectation. Questions on this? It's a very clever algorithm. It's a clean algorithm, but it's a super clever algorithm. Once again, let's stare at the algorithm. We had this outer and inner face. So the inner face is very clean. It just decodes, but then it comes up with these confidence probability measures. And then it's using these measures, it's going to erase some of the symbols. And now that helps it to go all the way up to DD by 2, unlike DD by 4, which the vanilla decoding did. Questions? Yes, a few faces I see here seem quite surprised. I can't see the expressions on your face. I don't know. Okay, I need a vocal feedback. Fine. Okay. Okay. So given that this is okay, let's now I'm going to try to get rid of the randomness in the algorithm. Notice randomness was crucial, in which we decided how to erase whether to erase a coordinate or a whole symbol or not. We use the confidence measure. So we will reduce the randomness in two phases. First, we will first reduce the number of randomness, and then say, if it's this much as a randomness, actually we can do this deterministic. That's how we are going to do it. So let me rewrite the algorithm. So next is going to be reducing randomness in GMD decoder. So let's look at the algorithm again. The inner face will remain as before. Copy. So actually, so I'm just going to modify the outer face. So let me just cut and paste only the outer face. The outer face was the one which had randomness. And what are we going to? So this was the outer phase. If you recall, we used the confidence measure to erase this one. Now we tossed a separate coin for each of these outer blocks. For all the capital N blocks, we tossed a separate coin with a suitable bias. Each one was of a different bias to do this. What we'll say is we can toss one single real number and use that to get, because it was, if you looked at the proof of it, it was just linearity of expectation that was used in the proof. Therefore, you didn't need to use independent random coins across the different blocks. You could have used the same random coins, and the proof and the analysis used only linearity of expectation. So as the analysis used, used only linearity of expectation, use common randomness for all the n blocks. That's going to be the idea. So that's the goal. The idea is going to be this. So how am I going to implement this? Implement this following fashion. That's one. The outer phase. So the outer phase, we will first choose theta to be a uniform random number in 0 and 1. Just pick a uniform random number. Then for each this one, what we will do is, instead of doing this, if we'll set this to be, if theta is less than 2 ei by d, we will set it to be erased, and otherwise we will retain it as it is. Notice this is exactly the same thing as the previous algorithm. Of course, these are no longer independently flipped, but that didn't matter. The analysis worked with linearity of expectation. So even this outer phase will this outer phase will also just work. So I'm going to draw this. Let's see. This works. Yeah, so that's the algorithm. So that's the outer phase. So I've eliminated randomness across the outer phase. So basically, what are we doing? We're using a particular threshold. We are picking a random threshold from 0 to 1. And for everything which has confidence, which has this confidence above the threshold, below the threshold, we erase it. Beyond it, depending on where this threshold happens, we are going to erase the coordinates. Above, below is this one. So we choose a threshold. We'll look at all the probability, all the confidence measures. Which of them are lower than all the ones which are above this threshold, we're all going to erase them. Everything which is below the threshold, we'll retain it and do the decoding only on that part. Is that fine? Now notice, do we really need a random threshold to do this? How many thresholds can be there? There can be only as many thresholds as the number of number of blocks, because you have at most one guy for each block. It doesn't matter which theta you pick. As if you pick a theta in between two EIs by D, you're going to get the same guys. You're going to erase or decode. So you only need to run this for certain thresholds. You don't need to run it for all the thresholds between 0 and 1. You just need to run it for corresponding to every. So you can further observe that the above algorithm is unchanged if theta is between two successive EI by 2 EI by D. 2 successive, I don't mean successive in 2 E4 by D and 2 E5 by D. Just put all the 2 E5 EI by Ds on the number line and successive that sense. As long as it's between the two thetas, it doesn't matter where it is. So now you could now further modify the outer phase as follows. The outer phase. You do the following. Let capital theta be all the 2 EI by Ds, I in N, and let's also add in the two extreme thresholds, 0 and 1. Now for each theta in capital theta, do this to obtain what I call m tilde theta. So you do this for every theta, and then finally output the m tilde theta, which is the arg min over all theta in theta such that of the distance of m tilde theta to the residual. So let's write this. It is the composed word of m tilde theta and the received word. That one should work. There'll be one of the thetas will work. Just run it over all the thetas, run it over all these distinct thetas, run it, find it out, and then just output that guy. So that's the entire algorithm. Fair enough. Is the GMD decoder clear? Now it's a completely deterministic algorithm and does what we wanted it to do. It's extremely simple, but it's an extremely simple, but very clever algorithm. Questions? Okay. If you haven't seen this algorithm, you should be surprised that it works out so nicely. The inner face is as before, the outer face will only be modified this way, and this is the outer face. Questions so far? If this is fine, we will change topics and move on to a new topic. Theta star, so the theta star is argument of questions. Or if you follow it, somebody say that you know this one so that I can go on to the next topic. Ishan, you had something to ask, or
The last part, outputting this theta step, can you go over it again?
which part? This one?
The final last, yeah.
So you're running it for each threshold theta. Now, you know there is a threshold theta. You know on expectation, it works. Therefore, there is a threshold theta that works. It's just that I do not know which threshold theta that is. So for some other theta, you might have either erased too many things or not this one. something could have gone wrong. I do not know if the outer Y will even work on it. So you just recover for each one of them. One of the theta should work. And only one of the thetas will actually be close to the received word. There can't be more than one of them which is close to the received word.
Fine, yeah.
Yeah, that is all the previous analysis shows that an average theta works. That's what the previous analysis shows. Therefore, in particular, there is a theta that works. Now you don't know which theta, so you run all the thetas and then find out which of those thetas is the correct object. There can't be two thetas. They can't. There could have been two thetas that worked. That could be the case. That I don't care. But they can't. The corresponding m tilde thetas for those two thetas will have to be the same guy because you are less than the unique decoding radius. The corresponding two messages should be the same.
Right.
So you just pick one of them and do it. Or either that way or after each run of theta, after each run of this, just check that the corresponding m1 tilde is dd by 2 close to the received word. If it is, just output that and you be done with it and don't go on to the next theta because you know only the first time you receive one, you know that's the answer. There might be another theta also that works, but this theta is good enough. You could do either of them. Yeah. Fair enough. Okay, so then we'll take a break from this. We will change topics. We'll change gears completely. We are going to go on to a new topic, which are called. So it will be a new topic called graph-based codes. And so where is the motivation for this thing going to come from? So already notice one of the goals of the course, we wanted to construct good codes, and we already constructed it using Reed-Solomon as the outer code, concatenating using Forney's concatenation with, say, the Wozencraft ensemble and getting these codes. We got already good codes, and for good super explicit codes also we got process. The question now we would like to ask is, are there other codes which also we can get such? So we would like to lay our hands on other codes, and are there simpler constructions which are not necessarily use code concatenation? Of course, code concatenation is a very simple, nice object. It's good to have it. But what I would like to know is, are there other objects in which I can construct a good code directly? I don't have to go through this concatenation, go through to a larger code and then come code over a larger alphabet and then come down to the Boolean alphabet and all. Can I directly construct a code over the large code, over the Boolean alphabet? This is a question which we would like to ask. That's one reason for. So we would like to ask, are there alternate constructions? And it's always good to have alternate constructions which match this one. They might offer some other advantages. In fact, one of the other advantages we will see later on for these codes is we will construct codes based on graphs. And these codes will have constant rate and constant fractional distance. We already constructed such codes using code concatenation, Reed-Solomon code, and all of this one. But the thing in which these codes, we won't do this in this lecture, later on we'll see, is because these are graph-based codes, there's a possibility that these codes can have linear time decoders and linear time encoders. Typically, the polynomial-based codes, you have to do some interpolation or something all the time. And interpolation typically takes, there's an FFT or something involved in it, and we don't know FFT runs in linear time. It runs in nearly linear time. It's n polylog n. Sometimes you would want to shave off that polylog n factor also. Can we get linear time codes? And this was actually achieved. So this area was sort of, there are three important pieces of work here. The first is due to Gallagher, who defined Gallagher from 63. Yeah, Gallagher 63, who was the one who sort of more or less initiated this study of graph-based codes. Then later on, Tanner sort of generalized it and said there are far richer family of codes. And eventually Sipser-Spielman and Spielman. These are the four main papers. So this is 94 and this is 95. These are the four main papers. This I won't go into telling which paper did what. We will finally talk about the whole result or the combined result which we have. But we won't go into what. So but these are the main players in it. There have been lots of work in this, but these are the prominent people who contributed to this. So the first thing, so what are graph-based codes? What are graph-based codes? I want to say this is actually a very let's work just over codes over the binary alphabet or Boolean alphabet. Now, and furthermore, let's work only with what are these things? So what are these objects? So I want to work with, suppose we are working only with linear codes, GF2 linear codes. Let's focus our attention fully on these codes and see a graphical representation for these codes. We already saw there are two representations for linear codes. What are the two representations that we have seen? The generator matrix and the parity check matrix. So what I'm going to do is take one of these representations, namely the parity check matrix, and give it a graphical presentation. That's all. So it has a parity check matrix representation. And what was this representation? So we had this matrix H, which is a M by N matrix, and M is typically N minus K. And it's going to check if this object is 0 or not. So in particular, the code was equivalently defined as set of all x in 0, 1 to the n, such that hx is 0. That was our parity check viewpoint of the code. The graphical representation is just going to be, we're going to take this parity. It's going to be actually something super simple. We're going to just take this parity check and represent it as a graph. What am I going to do? So we're going to view, what are these? We're going to view each of these as these are the variables. And you're asking, do the variables x1, x2, x3, xn satisfy some constraints? What is a constraint? Each row of this is a constraint. It's basically asking, is the dot product of this row with this constraint 0 or not? That's the constraint we are asking. So we're going to represent this as a graph in which we'll call the factor graph of this particular code. Factor graph of the code C is the following very simple guy. On the left-hand side, it's going to be represented by a bipartite graph. The left-hand side L will exactly be N. These will represent the block locations x1, x2, up to xn. And the right-hand side of this R will represent the M rows or constraints in the parity check matrix. Okay, so you're going to have a constraint for each. So this is H1. So let's put it on the superscript. H1, H2, all the way up to HM, where what is H? HI is it. So this is like H1 is this row. H is this matrix. H2 is this row. HM is this row. So I'm just putting it this way. And what I'm going to do the obvious thing. Then what's the edges I'm going to put here? Exactly corresponding to the ones in, which are the variables that participate in this constraint. Those are the edges I'm going to put in. So in particular, I will put ij. So I should put the edge ij among this one, if and only if Ji is non-zero. Okay, so that's the entire. So the graphic, the factor graph of it is this matrix LRE. So it's nothing. So far at this point of time, I have just rewritten the parity check matrix as a graphical viewpoint. There's nothing that has happened so far. I've just drawn a graph. And what we want to now ask is, if I give you such a bipartite graph, of course, just like a particular linear code has several parity check matrices, there are several factor graphs corresponding to a particular linear code. It's not a unique representation. There are multiple representations. What we would now like to ask is, can I tell you some properties of the factor graph? Now I could define the graph just like parity check matrix was sufficient to define the code. If I give you the factor graph, that will tell you what the code is, because the code is exactly, you pull out the parity check matrix from this code and this. What is the code? The code is exactly, you're stating that it's all those locations. So if I give you a graph G, LRE, the code corresponding to CG is exactly those X in 0, 1 to the L, such that for all R and R, summation X, what should I write? X, L in the neighborhood of R is 0. That's exactly the code. I've just rewritten the parity check matrix in a different format. That's the code. So we are now going to turn the question and ask, can I identify some properties of this bipartite graph that will make this code have good rate and good distance? So that's the question we are going to ask. Is there properties of this bipartite graph that I can identify in order for this code, the code that arises out of this, basically this code? For it to have good distance and good rate. Is the question clear? I've just restated my problem. I haven't changed anything so far. I just restated the problem. It's just that possibly because we understand graphs a little better, can I identify a property of the bipartite graph? So the underlying graph has some property. Can I show that the corresponding code that I construct this way will have good rate and good distance? That's going to be a question. And we'll show actually we can identify a very nice property of the graph, which is going to guarantee rate will be actually very simple. We'll see rate in the next 30 seconds. We'll see what rate is. Distance is going to be the complicated object. We'll realize that there's a property of the bipartite graph. If it is true, it will guarantee distance. And next lecture, we'll say it not only guarantees distance, it actually also guarantees a linear time decoding algorithm for the graph. Okay, so let's start off with distance first. Let's start off with rate. Rate of this code, rate of CG. This will do the most natural thing out here. Each constraint on the right reduces. So initially we start off with an unconstrained system. You can choose any x1 to xn. Every constraint on the right reduces the dimension by 1. It's one linear constraint. Therefore, what we know is the dimension of CG is at least size of L times size of R. So it's at least n minus m. So as long as this bipartite graph is such that m is constant fraction smaller than n, you do get rate. So as long as, if m is less than or equal to 1 minus r times n, then rate of CG is at least r. So we will look at bipartite graphs, which are these sort of lopsided graphs. It takes n vertices, the number of constraints is say n by 10 or 0.9n or something. Each of that, as long as it's a constant fraction smaller, that constant fraction, whatever by what ratio it is smaller with, that is exactly the rate. So rate is just going to be this trivial observation, and we won't do anything more for rate. Is that fine? So rate is easy. So rate, all that we wanted for rate is we're going to work with bipartite graphs in which the number of constraints on the right-hand side is significantly smaller than this one on the left-hand side, number of variables on the left-hand side in the factor graph. So as long as we pick such a graph, we always are guaranteed rate. The question is what happens with distance? Even before I go to distance, I want to just say what Gallagher and Tanner did in the process. What Gallagher was originally interested was, he was interested in asking, so if you recall the Hamming code, the Hamming code also had a bunch of hedges, but from using these constraints, using which of the constraints are satisfied and which of the constraints are not satisfied, you could identify, you could do the recovery. This was what the Hamming code had. This one basically, if you basically looked at h of x, this one for a code word, if x is a code word, h of x was 0. For non-code words, as long as the corruption is only 1 bit flip, this h of x will be a thing which will identify to you what is the code, what is that erroneous location. So Gallagher was motivated by, are there graphs for which I can have similar such properties? And what Gallagher observed was, if these things, if the arity of these guys was very large, then the fact that it is, suppose this particular constraint was violated, that means one of these guys have to be flipped in order to make this constraint satisfied. Now, if this was a very large arity, that doesn't tell you much information, but you could think of graphs in which the degree over here is a small degree. In which case, if this is an unsatisfied constraint, you know that only one of these guys have to be flipped. Of course, flipping it might cause other things also to get unsatisfied. It will satisfy this one, but it might unsatisfy something else. But so he instead said, let's work with, so Gallagher's first observation was, let's restrict our attention to bipartite graphs whose right degree is bounded, right? That is the constraint degree. And this is what he called as low density. You might have heard this word, parity check codes, LDPC codes. LDPC. And all that it is stating is that parity check constraints are sparse constraints. The right degree is bound. That's all it says. So Gallagher said, let's work with these sort of codes, bipartite graphs. In fact, he said let's not only bound the right degree. Let's now notice, because you have the so in particular we might work to make things nicer. We'll work with things which are actually regular from the right. The right degree is not just bounded; it's the same degree. It's a D on one side. Now notice the left side and the right side differ only by a constant fraction of each other. Therefore, if the right degree was a constant, if the graph was regular on the left side, the left degree is also a constant, because the left degree into the left side is equal to the right degree into the right side, because the number of edges, whether you count from this side or that side, is the same. So this will sort of motivate us to define what we'll call these sort of, we'll say G LRE is CD regular if the left, that's the variable degree, is equal to C, and the right constraint degree equal to T. So we'll work this one with such sort of, the left degree is C, the right degree is T. Work with this. Sometimes we might work with what, instead of putting C and D, we will just say CD bounded. That is just if the left degree is less than or equal to C and the right degree is less than or equal to T. Okay. And what Gallagher proved, which we will not prove in class, is the following. He showed that a random LDPC code that is obtained by picking a random CD regular graph. Attains the GV bound. So this was a theorem that Gallagher. That is, pick a random, by the way, you can ask, how do you say pick a random CD regular graph? Or how do you pick it? What Gallagher did was the following this thing. So he picked a random permutation from Cn to Cn. So sigma is a random permutation. Okay. So how does, and now let's list out these elements as these elements. These are Cn elements over here, Cn elements over here, and you have a permutation that goes this way. What did Gallagher then do? He just said, let's club every block of C and identify it as one single vertex. And every block of size. So say, let's choose D to be such that Cn by, let's choose M to be such that, let's see be such that D times M is equal to C times N. So he will combine D of them from this side, this one. So you get a graph which has the left degree is C, the right degree is D. Of course, this is not a simple graph. There might be multi-edges, but I don't care. In the constraint, basically, if there are two things this way, he will actually, those two constraints will just cancel out each other in the parity check matrix. So it will be a CD bounded graph rather than a CD regular graph, but that's fine. So this was the distribution that Gallagher picked, and he showed that if you pick a random such graph, the corresponding factor code that you obtain from it achieves the GV bound with high probability. People with me on this?
Exactly,
So as C goes to infinity, it achieves the GB bound as C goes to infinity. Yeah, exactly the GB bound. Okay, so that was what Gallagher did. What did Tanner do after this? Tanner said, so we had this bipartite graph construction, L, or we had these constraints over here. So this is the N variables and the M constraints. Tanner observed, and what is the constraint that we are putting over here? The constraint that we are putting over here is the fact that the constraint that is put over here is if this variable was R and R, we are setting that summation XL, L is a neighbor of R, is 0. So what are we setting? The neighbors of this code should have even parity. Of this of every right-hand constraint vertex should have even parity. Now Tanner said, why should we this is just stating this is you're putting a code here. I could have put an inner code. I could have started off with a code. So Tanner suggested the following instead. Tanner said, let's see small c be a say DL some delta D2 code. And what he'll say is basically so the Tanner of G and the C is basically the set of all X in 0, 1 to the L, such that for all R in R, we have that if you look at the restriction of X just to the neighborhood of R, this should be a member of C. That is, if you look at this local view of this, whatever you see, this local view, that should be the code from small c. The previous Gallagher construction was the previous the case in which the previous case which we said C of G is exactly Tanner G, and we put the even parity code. So Tanner said you could construct a richer family of codes this way. Notice this is also LDPC because the constraints can only become smaller. The constraint, if the previous one was an LDPC code, this continues to remain LDPC code. It's just that each constraint now is not, each right vertex is not a single constraint, but as many constraints as defined by that particular code C. So it's previously we reduce the dimension by 1 for each of them. We'll have to reduce the dimension by the corresponding 1 minus R times D for this, but that will be the number of constraints each particular right vertex is imposing. So Tanner said you can work with this richer family of codes and still manage to do things. But still, this doesn't answer distance and all. All of them work with random codes and this one. The key insight of Sipser-Spielman is the following. Sipser and Spielman is if the bipartite graph is an expander, rather is an expander, then if the bipartite graph G is an expander, C of G, rather, write it this way. What they showed is the following: expansion guarantees distance. So we'll have to define what expanders are and stuff. I will define that shortly. They identified a property of the bipartite graph. They showed that if the bipartite graph has this property called expansion, then the underlying code will have good distance. In fact, they will prove two set of results. They'll prove firstly, very good expansion. Rather, let me write it this way. G is a very good expander. We'll have to define all of these, what an expander means, what very good expander, all of these mean. Then there's the Gallagher, the original construction. C of G has distance. Now, they also showed that you don't have to be a very good expander. Even if you are just mildly an expander, this is G. G is an expander. Then they showed that the Tanner graph corresponding to G and a suitable choice of inner code has distance for certain choices of inner. Okay. We will formalize all of this shortly. So this is Sipser-Spielman. It's a remarkable result. It's a remarkable result for this one, and that's their key takeaway. Okay. Questions? So is it okay if I take 10 more minutes? I just want to define what expansion is and then they'll stop. Okay, so let's just define what's expansion. So once again, I'm going to work with bipartite graphs. So I have L. So let's define expansion. Expander graph. For now, I'll just define it with respect to bipartite graphs, but expansion can be defined even for non-bipartite graphs. So I'm given G, which is L, R, and E. So this is L, and size of L is the size N. This is R. Size of R is M, and there are edges across. Let's assume G is CD bounded or CD regular. We will say G is delta A expander if the following happens. For all subsets of L, of size, as long as mod S is not too large, it's at most delta fraction of the right-hand side. If you look at its neighborhood, look at all its neighbors. So this is S, this is gamma S. That implies gamma S is significantly larger than S. Gamma S is at least A times size of S. So all small sets, all sets of size up to delta do expand by a factor at least A. This is what I mean by G is in. And I'm asking for expansion only from one side. Is this okay? So notice once again, what is gamma? I've been using this. Gamma S is the set of all J in L such that there exists edge ij in E and I in S. That's all I mean. Heh. What? Yeah, sorry. J and yeah, J R. Yeah. Right. Hmm. And how large can expansion be? What's the largest expansion we can hope for?
At most,
At most left degree. So in this case, at most small c. So when I mean something is a very good expander, I mean something whose expansion is this capital A is very close to C. If just expander means I can guarantee some A which is larger than 1. A which is larger than 1 means it's expanding. A which is very close to small c means it's a very good expander. So that's going to be the difference. That's going to be the differences between these two, between 1 and 2 over here. Okay. And notice now we are looking at these bipartite graphs. So suppose the following two definitions is going to automatically motivated by the fact that we are going to come up with constraint graphs and we're looking at factor graphs and stuff. Suppose I put a code word over here. I put some set of variables x1, x2, xn, which is a potential code word or some received word. If it was a code word, every constraint is satisfied. If it's not a code word, there are some constraints here which are not satisfied. Are these so every constraint? So let's look at the ones of the code word. Everything that is not satisfied is a neighbor of the ones. So let's assume S is the set of ones in the code word. Everything that is not satisfied has to be a member of gamma S. But gamma S could have both satisfied because everything outside is not a neighbor. It's going to only see zeros. So they will be automatically satisfied. The only things that have possibility being violated are the ones in gamma S. But which are the guys which are in gamma S that are violated? Is it all of them are violated or only those vertices in gamma S are violated which see an odd number of guys into S. So this will motivate the following definition. So I will define the following other neighborhoods also. Gamma odd of S is the set of all J belongs to R such that there exists an odd number of i's in S and ij. Basically, it's a set of guys which have its neighborhood into J is odd. Let me make it even more. This one. All I mean is gamma J intersection S is odd. We'll define one more. This is a sort of an ugly thing to work with, the odd neighborhood, which are odd, this one. So we'll work with something called the unique neighborhood. J belongs to R. It is such that gamma J intersection S is exactly of size 1. It's called the unique neighborhood. It's those neighbors of S such that they have only one neighbor into S. All the other neighbors are outside S. Notice that certainly, what do we know? Gamma plus S is contained in gamma odd S is contained in gamma S. Because the unique neighborhood is certainly a subset of the odd neighborhood, which is certainly a subset of the entire neighborhood. Now we'll make one simple observation. If G equals LRE is a delta A expander, then it is a delta 2A minus C unique expander. Now, what is a unique expander? I haven't defined a unique expander. It's exactly the same definition. That's G is a delta A unique expander if for all S subset of L, if mod S is less than or equal to delta, it's not too large a set, then the unique neighborhood of S is at least A times size of S. Okay. Now, why is this claim true? Where G is, let's assume Z is CD regular. I think bounded is sufficient. We had this is S. So let's look at the neighbors of S. The neighbors of S are of two types. There are the unique neighbors, and then there are the, let's call them the things which have at least two neighbors into S. So U is equal to gamma plus S, and U disjoint union with T is equal to gamma, rather T is gamma S minus gamma plus S. Now, this is just a fact. We want to show how large U is. I want to say the graph is a good expander. What does the statement say? The graph is a good expander. And if this expansion is larger than, so for example, for this theorem to even make sense, A should be larger than C by 2. Or A should be strictly larger than C by 2. Otherwise, there's no meaning in this. Otherwise, this 2A minus C becomes a meaningless statement. Want to show. But this is a trivial fact. Let's just count the edges from both sides. What's the number of edges? So what do we know? We know that U union T, the size of this is at least A times size of S. That's just expansion properties. Now let's count the number of edges. Count number of edges between S and gamma S. So from the left side, we know that the number of edges is less than or equal to C times size of S. From the right side, we know the number of edges is greater than or equal to each of the unique things contribute one edge, and everything else contributes at least two edges. Therefore, what do we have? We have mod U plus 2 mod T is greater than or equal to C mod S. Now let's just, that is mod U plus 2 times, this is, what is T is, this is size of gamma S minus something is going wrong somewhere. Sorry, this inequality should be the other way around. Yeah, because this is a lower bound on the number of edges, this is an upper bound on the number of edges. So we have this, so minus gamma S minus size of U should be less than or equal to C times size of S. Therefore, size of U is at least 2 times gamma of S minus C times size of S, which we have, because gamma, this is an expansion, this is 2 times A minus C of S. I've done nothing over here. It's a very simple, it's just counting edges from both sides. Therefore, if something is an expander, then something is a unique expander. Now, okay, I'm not going to do much. I'm going to say if something is a unique expander, I want to say, suppose a graph is a unique expander. Just look at, let's make the simple observation. If GLRE is a delta A unique expander for any A greater than 0, then I want to claim that then CG, the distance of CG is at least delta. Why? This is a very simple observation I want to say. I just take this bipartite graph. It's a linear code. So let's take a weight of the minimum non-zero code word. If it has distance less than delta, if the number of coordinates is less than delta, let's look at S being exactly the non-zero, the weight, the one locations in the code word. If this is less than delta, you know it has a unique neighborhood because A is non-zero. But if A greater than 0. But if A is non-zero, that means there is at least one constraint that's violated. Therefore, there cannot be any code word which has less than delta n ones in it. Every non-zero code word has to have more than delta n ones if it is a unique expander.
What if A is less than C by 2?
No, this is a unique expander.
Any lower bound for U.
Sorry, Srijata, I didn't get you.
You got the lower bound that unique neighborhood is at least 2A minus C times mod of S.
Here the A
But
minus
if A is less than C by 2, you don't get any lower bound from this.
So I don't get anything. No. So that is if the usual expansion is more than C by 2, then the unique expansion is 2A minus C. Here I'm talking about unique expansion A. So this A is actually 2A minus C.
Yes.
So in other words, further corollary, if a graph is a further corollary of this will be if G is a LRE is a delta A expander for A greater than C by 2, then delta CG is greater than delta.
Yes.
Yeah. Okay, just to make things clear, then let's put this as A plus and A plus. That's one. Yeah. So the property we identified is if a graph is an extremely good expander, the maximum expansion is C. If it's at least C by 2, strictly larger than C by 2, then the underlying graph will have distance. And the distance will exactly be the delta up to which you can guarantee expansion. That's the property which, this is the very simple observation, but fundamental observation that Sipser-Spielman observed. What we'll do in the next lecture is understand this in more detail and see also a decoding algorithm for such expander class. Okay. Yeah. So the summary of this is basically if the underlying graph has expansion, in fact, if it has very good expansion larger than C by 2, then the corresponding graph that you get out of it, corresponding code you get out of it has distance up to size delta, where delta is the set up to which you can have expansion. Of course, Sipser-Spielman also asked the question, suppose expansion, you don't have it all the way up to C by 2, you have only smaller than C by 2, what can you do? Then they will show some other results, which we'll see in the next lecture. But for now, this is just to tell you that expansion is sufficient to guarantee distance. So now we have transferred the problem of constructing good codes to constructing good bipartite graphs, which are good expander graphs. So if I can construct a bipartite, a lopsided bipartite graph, which is a good expander graph, then from it immediately we get a good code. Okay. I've already overshot a fair amount. Let's stop this. You can stop the recording.